Okay, welcome to the first lecture of this course, and we want to begin by reviewing some of the basic concepts of linear structural analysis. So, what is the process of structural analysis? As you know, when you want to analyze the real world structures, we have to create an idealized mathematical model, because the real world structure cannot be analyzed exactly. Okay? So, you have to create idealized mathematical model. Very often a 2D structural model is adequate. Okay? So, that depends on the situation. What we do after we create a model, we apply the loads. Okay? The loads could be static load or dynamic load, for example, earthquake. So, it depends. Then the next step is the actual computation, where we perform the analysis of the model. The analysis could be of two types. You can do a static analysis, you can also do a dynamic analysis. Once the analysis is done, the idea is to interpret the results, study the internal forces, deformations and deflections. Okay? What are the internal forces? Axial force, it could be shear force, could be bending moment, could be twisting moment. At the end, I want to emphasize that we have to understand the behavior of structure, okay, and develop a feel for it. So, that is basically the way structural analysis is done. There are three key steps: idealization and modeling, the computation, and then the interpretation. So, these are the three key steps of any structural analysis process. Okay. So, I want to review the basic requirements of structural analysis, that is the equilibrium. Okay. How do we explain equilibrium? So, consider I have a body in a two-dimensional space. So, let us say this is a planar body in the xy plane. Okay. It has three rigid body modes. It can go in the x direction, it can go in the y direction, and it can also rotate, right. So, there are the three rigid body modes that are possible for a planar body. Okay. For equilibrium, we must restrain all the three rigid body modes, right. So, how do we do that? So, let me draw it. So, let us say here is a body. Okay. This is my x axis and this is my y axis. So, this body can move in the x direction, can translate in the y direction, as well as it can rotate. So, for equilibrium, we must restrain all the three rigid body modes. So, what I will do? I will put a roller support here, right. So, that means the motion in the x direction is restrained. I will put another roller support here, then the motion in the y direction is restrained. But what about the rotation? Well, if you see that these two reactions are concurrent, they are intersecting here. So, this can rotate, right. So, I need one more restraint to prevent this. So, what I will do? I will erase this and make it a pin. So, that means now I have introduced two restraints here, one restraint here, I have introduced three restraints, and then all the three rigid body modes are restrained. Okay. So, we need at least three restraints, as I explained. What are the equilibrium condition? Summation Fx is equal to 0, which will ensure that there is no resultant force in the x direction. So, translation along x direction is restrained. Summation Fy is equal to 0. So, which ensures there is no resultant in the y direction. So, motion in the y direction is restrained, and summation Mo is equal to 0, which ensures there is no tendency of the body to rotate. So, there is no resultant couple moment. Okay. What is this point O? The point O could be any point on or off the body. So, these three equations are necessary and sufficient conditions for equilibrium in two-dimensional bodies. Okay. There are alternative forms of equilibrium equations also. So, this is the one that I wrote in the previous slide. Okay. The alternative ones are, you can do summation Fx is equal to 0, summation Ma is equal to 0, summation Mb is equal to 0. The only requirement is that points A and B must not lie on a line perpendicular to the x axis. Okay. I would like you to derive it and check. I am sure all of you will be able to do this. Another alternative could be, I can take moment about a point A, moment about a point B and moment about point C. The only requirement is that A, B, C must not be collinear. Okay. For a body in 3-dimensional space, the necessary and sufficient conditions are this: to prevent 3 translation along x, y and z direction, and to prevent any rotation. So, summation mx equal to 0, summation my is equal to 0 and summation mz equal to 0. As we all know, to apply equilibrium equations, we have to draw the free body diagram, which I am sure all of you know how to draw free body diagram. Now, let us briefly review stable versus unstable structures. So, when one or more rigid body modes are unrestrained, then the structure is unstable, otherwise it is stable. Okay. For a coplanar structure, there are at most 3 equations of equilibrium for each free body or each part of the structure. So, if let us say there are n parts in a structure and r unknown reactions, so each part is giving me 3 equilibrium equations, right. So, I can say if r, the number of unknown reactions, is greater than or equal to 3n, okay, then it is a necessary but not sufficient condition for stability. This r greater than or equal to 3n does not mean the structure is stable. I will show you as an example. But if r is less than 3n, number of reactions are less than the number of equilibrium equations available. Okay. So, then it is sufficient to say that the structure is unstable. Okay. So, let us do some example. So, here the first one is basically a simply supported beam, but I have introduced an internal hinge here. Okay. So, what I will do, I will cut this here and draw the free body diagram. So, if I draw the free body diagram, what do I get? So, here I have got 2 unknown reactions. Here at the hinge, I can draw like this, okay, 2 unknown reactions. And then if I continue, so equal and opposite is acting here, here, and then you have that. Okay. So, how many free body we have? We have one free body here, we have the another free body here, right. So, for each, how many equations of equilibrium we have? So, for n is equal to 2, okay, and r is equal to how much? So, we have 2 unknown here, 2 unknown there and 1 here. So, 2 plus 2 4 plus 1 5. Okay. So, how many equations of equilibrium? 3n is equal to 6 and this is greater than r is equal to 5. So, this is unstable. This is unstable, which is also easy to understand. If you apply some load, okay, if you apply some load somewhere, what will happen? This will move and it will form a collapsible mechanism like that without offering any resistance. So, that is a rigid body mode of displacement. On the other hand, let us take this example, the second example, where what I have done, I have introduced a pin support on the right hand side. So, this is not allowed to move anymore. So, as you can see, we had earlier n is equal to 2. So, if I cut it here, again I will have n is equal to 2 and r is equal to, earlier we had 5, now we will have 6, because there will be 2 unknowns here, 2 internal reactions here and then 2 here. So, that is 6. Okay. So, here 3n is equal to r. Okay. So, that means it is stable? No, it is not stable. Why? What will happen? If you draw the free body diagram, you will see that, let us say this is the left side and this is the, let us do it like that, this is the right side, okay, right. Now, you consider, you apply any load, okay. I will let you try this, you apply any load here, okay, and consider the equilibrium, right. So, if you take moment about this point, right. So, what will happen if you take moment about this point, this force is not producing any moment, this force is not producing any moment, this is not producing any moment, only you will have the moment due to this force and this force, right. Okay. So, once you do that, then you let us say determine some value for that, right. So, let us say I will call this R. Okay. So, the same R is acting here, right. Now, if you consider equilibrium of this free body and take moment about this point, what happens? Then R times this lever arm is not equal to 0. So, that means R must be 0. That means this must be 0, that means this is not in equilibrium, right. So, there is a conflicting situation if you apply statics. Okay. Why is this happening? Because as you can see, if you apply even the smallest load, this is going to form a collapsible mechanism. So, although R is equal to 3n, this is unstable. Okay. This is unstable as long as we consider the equilibrium in the undeformed configuration. This is what I have done. I have considered the equilibrium in the undeformed configuration. But when we actually get into nonlinear analysis, you will see that I can write down the equilibrium equations for this case in the deformed configuration, and then as we can see, I mean from reality also, that if I apply a little bit of load, okay, it displaces, and then as I keep going on, okay, as I keep increasing the load, it can take load. So, but that you can do only if you perform a nonlinear structural analysis. Okay. On the other hand, I will let you do this one. What is it? It is nothing but a propped cantilever with an internal hinge, right. So, I will briefly write here, we have got 3 unknowns here, we have got 2 unknowns here, and we have got 1 unknowns here, right. So, how many total unknown? R is equal to 6. How many free body? Well, you cut it here, that is how you got 2 internal forces here. Okay. So, n is equal to 2. So, that means 3n is equal to R. So, this is statically determinate and stable. Okay. Now, you can also have partial restraints. Partial restraints means you have less restraints than necessary in a part of the body or in the whole structure. For example, I am showing you an a case where I have a beam A, C and B, and then there is a bracket, there is a body connected like this using a bracket. Okay. So, if I draw the free body diagram for this bracket, what do you see? So, let us say this is the load acting. Okay. So, this bracket is such that it will offer you vertical reaction and it will offer you a moment like that, right. Now, if I draw the free body diagram for the beam, so it is a fixed beam. So, I have this, let us say these are the forces at the ends, okay, right, and here I will have to apply equal and opposite, so that when you combine they should vanish. Okay. Now, what happens for this free body, for this free body diagram, how many unknowns are there? R is equal to 2. How many equations are there? So, n is equal to 1. So, that means R is equal to 2 is less than 3n. Okay. So, this is not well restrained. So, all the rigid body modes are not restrained. So, what will happen? This bracket can slide right or left, okay, can slide to left or right, right. So, therefore, this is partially restrained and hence it is unstable. So, CDE can slide, that is what I have written here. Consider another case of improper restraints. So, improper restraint, the number of unknowns could be greater than equal to the number of equations of equilibrium available, but all the rigid body modes may not be restrained. In that case, we call it improper restraint. For example, what I am showing you here is a beam which is supported on 3 rollers. Okay. These 3 rollers, the roller orientations are different. So, here it is like that, here it is like this, and here it is horizontal. So, if I draw the free body diagram, what do you see? You see that there is a reaction here, okay, and then here there is another reaction, and here there is another reaction, right. So, what is happening? All the three reactions are concurrent, they are meeting at point O. So, imagine now I am applying a load here, right, and if I take moment of this load about this point, then what is happening? Well, the moment balance is not being satisfied. So, then this beam will rotate about this. So, although we have three unknown forces and three equations of equilibrium, it is not properly restrained. So, this is an example of improper restraint, hence it is unstable. So, all reactions are concurrent and pass through point O, hence it is unstable, right. Another case is, consider this where I have a beam, okay, supported on 4 rollers. So, I have one reaction here, 2, 3 and 4. So, now R is 4 and number of equations of equilibrium is 3. Does it mean this is statically indeterminate? No. First of all, we have to see whether it is stable or unstable. All the reactions are parallel. So, if you just apply a load as I am showing, so then what will happen? This will move, right. This will move to the left. So, the translation is not prevented, it is a rigid body displacement, hence this is unstable. So, all reactions are parallel. Okay. So, what are the necessary and sufficient conditions for a structure to be stable? Well, first is R must be greater than or equal to 3n. This is a necessary condition, but not sufficient. It must not form a collapsible mechanism. So, no collapsible mechanism, and reactions are neither concurrent nor parallel, then only the structure is stable. So, these are necessary and sufficient conditions. Now, let us talk about determinate and indeterminate systems. So, what is a statically determinate structures? When all the forces can be determined strictly from the equilibrium equations, then we call the structure to be statically determinate. On the other hand, if we have more unknown forces than available equilibrium equations, then it is statically indeterminate. And we define the degree of static indeterminacy, which is equal to the number of unknown forces minus the number of equilibrium equations available. Recall that for each part in a 2D, we have got 3 equations of equilibrium, right. Okay. So, now let us do some example. So, classify the structures below as stable or unstable. If stable, determine whether statically determinate or indeterminate. If indeterminate, determine the degree of indeterminacy. Okay. So, let us begin with the first one. So, how do I solve this? Well, this is an internal hinge. So, what I will do? I will cut it here. So, if I cut it here and draw the free body diagram. So, for the beam, this is the free body diagram. These are the 2 reactions and one horizontal, one vertical and a moment. So, when I cut at the internal hinge is like this, right. So, it is allowing rotation. So, there is no moment transfer, right. So, there are only 2 reactions like so. Okay. And now, if I draw this part, this is hinge. So, I have 2 reactions here. Here I have to apply equal and opposite. Okay. So, how many total unknowns I have? I have here 3 plus 2 5 plus 2 7, right. So, I have got I have got R is equal to 3 plus 2 5 plus 2 7. Okay. How many free body we have? 2. So, that means R is equal to 7 is greater than 3n is equal to 6. So, this is statically indeterminate to the first degree. Okay. On the other hand, let us consider this example. So, here we have a roller. So, there is one reaction and this one we have 2 reactions. Okay. So, is it, first of all, is it stable? This example, what do you think? Is it stable or unstable? Yes, it is stable because R is greater than equal to 3n, that criteria is satisfied. The reactions are neither concurrent nor parallel and also there is no collapsible mechanism. Okay. Now, come to this example. Okay. So, we have got 2 reactions here, 1 reaction here, Are they the reactions, are they concurrent? No. Are they parallel? No. Is there any collapsible mechanism? No. So, R is equal to 3, N is equal to 1. So, R is equal to 3 is equal to 3 N. So, this is stable and statically determinate, whereas the left one is stable and statically indeterminate to 1 degree. Now, let us talk about this example. Okay. So, in this example, what we have one internal hinge here, another internal hinge here, right. So, how many unknown reactions are there? So, there is one here. Let us draw the free body diagram. Okay, like so, and then here, this here I have 2 and equal and opposite. Okay, that is it. So, how many free bodies? We have got N is equal to 3. How many reactions we have? Unknown reaction 1, 2, 1 plus 2 3 plus 2 5 plus 2 7. Is that correct? 1, 2, 3, 2, 5 plus 2 7. Okay. Then what is happening? R is equal to 7, R is 7 and there are 3 free bodies. So, this is less than 3 N, which is 9, right. So, there are 9 equations of equilibrium, but R is only 7. So, this is unstable. Okay. What will happen if you apply load to this? Let us apply. So, let us say if I try to pull it, what will happen? This will move and the structure will form a collapsible mechanism, and that is also apparent from this equation. So, this is unstable, right. Okay. Now, what about these examples? Some of these examples you can try. Okay. So, let us say here now I will write only like this. There are 2 unknowns, here there are 2 unknowns, right, unknown reactions, there is only one free body. So, N is equal to 1 and R is equal to 4, right. So, this is statically indeterminate to 1 degree. Okay. On the other hand, the second example here, so we have got 2 reactions here, 1 reactions here. Is that all? No, because to be able to draw the bending moment, shear force, axial force diagram for this, the second story, okay, it is a portal frame with 2 stories, right. So, to do that, what you have to do? You have to know the internal forces. How do you know the internal forces? Unless we cut it, we do not know. So, let us say if I cut it here, right. So, if you have any beam, let us say this is a beam, if I cut it, then how many internal forces are exposed in 2D? So, we have, let us say, let me draw it like this. So, this is the typical sign convention we take, left up, right down, okay, and then there is also axial force. Okay. So, this equal and opposite will be acting on this side. Okay. Similarly, here. So, this axial, then there is the shear and then there is the moment. Okay. So, how many internal forces are exposed when you cut it? When you cut it, you expose 3 internal forces. So, let me write 3 here. So, you have got how many unknowns now? R is equal to 2 plus 3 5 plus 1 6. How many free bodies? Well, if I cut it here, there is only one free body. So, N is equal to 1. So, that means this is statically indeterminate to what degree? R minus 3 N, that is 3 degree. Okay. Now, solve this problem? Well, I will let you do that. Okay. For a truss, so all this we have talked about is for beams and frames. So, for a truss, how do you study determinacy? Okay. A basic element of a truss is a triangle. Why is that? Because if I give you, let us say, any other shape, then that is not stable. Why? Imagine that I give you 3 pieces of some length to the entire class, let us say, okay. And if I ask you to make a shape, all of you will come up with this same triangle, because when I give you the 3 members, the triangle there could be only one triangle. On the other hand, if I give you 4 rods, let us say if I give you 4 rods, the same 4 rods to the entire class, the entire class can come up with infinitely many quadrilaterals, because it can take any shape. So, it is not stable, right. So, a triangle is a stable shape and is the basic element of a truss. Okay. How do we analyze a truss? We assume that the members are pin jointed by smooth pins, and all loads are applied on the joints. So, truss members therefore, are subjected to only axial forces. That is our assumption for the analysis. Okay. So, these are the assumption for the analysis. Okay. How do we study determinacy of a truss? So, let us say we have B bars and J joints and R unknown reaction in a truss. So, let me draw one. So, let us say I am drawing a simple triangle. Let me draw a truss like that. Okay. Right. So, how many bars I have drawn? 1, 2, 3, 4, 5, 6, 7, right. So, there are 7 bars. So, B is equal to 7. Okay. How many joints are there? 1, 2, 3, 4 and 5. So, J is equal to 5. There are 5 joints. Okay. How many unknown reactions are there? Well, here in this support we have two reactions. Here this is the roller support. So, we have 1 reaction. So, R is equal to 3. Okay. At each joint we have got 2 equations of equilibrium, summation Fx is equal to 0, summation Fy is equal to 0. What happened to the moment equilibrium? Well, the forces acting at a joint are concurrent and coplanar. So, therefore, the moment equilibrium is automatically satisfied, hence you have only 2 equations of equilibrium, right. So, therefore, for a truss, how many unknowns are there going back? So, you have B number of forces, which is 7 here. So, you have got B member forces unknown plus the reactions, which is 3 here. So, total unknown of 7. How many equations of equilibrium you have? You have 2 equations per joint. So, you have J into 2, right. That means, if B plus R is equal to 2J, it is statically determinate. If B plus R is greater than 2J, it is statically indeterminate. So, B plus R minus 2J, we can call it is the degree of static indeterminacy. But remember, this formula does not work all the time, which I shall show. Okay. So, if B plus R is less than 2J, that means the number of unknowns is less than the number of equations of equilibrium available, then definitely it is unstable. Okay. But if B plus R is greater than equal to 2J, does it mean it is stable? No, it need not be. So, a truss can be unstable even if B plus R is greater than equal to 2J. So, we should be very careful when we apply this formula. So, stability needs to be determined by inspection or a force analysis. Force analysis means you try to solve the problem using statics and you will end up getting conflicting results, which will tell that the structure is unstable. Okay. If a structure is unstable, then there is no question of whether it is determinate or indeterminate. Okay. So, let us look at some of the examples very quickly. Okay. So, in this example, in the first example, how many members are there? Okay. B is equal to 19, I have taken too many. J number of joints, okay. So, J is equal to 11, okay. And R is equal to, this is, there are 2 unknown reactions here, there is 1. So, R is equal to 3. So, if I apply the formula B plus R minus 2J, what do I get? 19 plus 3 minus 2 into 11. So, that is 0, right. So, this formula tells the structure is statically determinate, right. But before we go further, we have to see whether it can form any collapsible mechanism. Well, this is all made of triangles, so there is no collapsible mechanism, hence it is stable. Okay. Now, let us talk about this example. Is this is also made of triangles, but is this stable or not? Okay. Apply the formula. If you apply the formula, then you get R is equal to 3, B is equal to B is equal to 9, J is equal to 6. Okay. So, B plus R minus 2J is equal to 0. So, does it mean it is stable and statically determinate? Well, let us take a look. Okay. We should inspect it carefully, look at this internal one, right. So, in this case, if I draw the FBD of the internal truss, because sometimes you may have situations where this reactions, okay, the forces in this member can be concurrent. If that is the case, then it is unstable. For example, instead of this, if I just do a slight change, let us say I remove these members, okay, I remove these members. Instead, I connect them like so, I connect them like so, then what happens? The truss will become unstable, because if I draw now the inner triangle, okay, so this force, and this force, they are all concurrent, right. So, if you apply some load, the inner triangle can rotate. So, in that case, that would be unstable, but this is perfectly stable, no problem, and statically determinate. What about this case? Well, this case you can do and find out that B plus R is going to be, so B is 12, R is equal to 3, that is 15, and J is equal to, this is equal to 8. So, B plus R minus 2J, B plus R is 15, which is less than 2J is equal to 16. So, this is unstable, right. This is unstable. Okay. Thank you. That is the end of this lecture. We will continue reviewing this in the following lecture. Thank you.